Okay, folks. I've decided to give a mass description of where things stand with regards to grading. So this semester I'm going to experiment, and I'm not going to require those of you who got below 1 standard leave on the midterm to come and see me before I used to require it. I'll wait till the second midterm, and then if I have people who've not done well on both of them, then I'll ask you to come in. So today from about 2:30 or so till 4:30, I'm going to be in my office in 493 Quarry. In case after I give this brief presentation and after everything I've said in the first lecture, you still want to talk to me individually. So let's get rid of this. Or 493 Quarry. Between 2:30 and 4:30. Just drop in if you want to chat. And try to time it so you're at the 15-minute mark so that we have some semblance of order. Okay. Now, many of you are naturally concerned about where you stand in the class. So I want to show you how we've been doing in the past few semesters. This is the histogram for the grades from fall '06. Now, if you look at the paragraph above, I think making this full screen was not a hot idea because I need to zoom this in. I told you at the start of the semester that if you go to the EECS website and you type in grading policy, you'll come across a couple of pages that describe the guidelines that the department gives us in terms of what to do with grades. So here's the paragraph, right here. Okay, it says a typical GPA for lower division is 2.7, and they give a suggested distribution of grades. For example, 17% A's, 50% B's, and so on. And I also told you at the start of the semester that I take liberties with this policy because the next line says anything outside of 2.5 to 2.9 is considered atypical. Now, since I don't want to be atypical in more ways than I already am, I try to pin the class GPA at or about 2.9. There are people who actually who keep track of these things, and so I don't want to be tapped on the shoulder and asked why I'm consistently giving higher GPAs than the department would like. This, of course, is to fight grade inflation. That's the general philosophy. Okay, so the way I work out the 2.9 is through this distribution of grades. I'll post this on BSpace, so you don't have to take notes on this. I'll post the PDF file later on BSpace. What a bunch of geeks. Actually taking notes on this. So I didn't want to fine-tune it any more than necessary, so I'm not showing the plus-minus grades. But you have to understand that all these grades on the left column include the pluses and the minuses. So when I say percentage of students who got A's is 35, that includes any type of A minus, A, and A plus, not just the middle grade. And so you see that it's much more generous than what the department suggested. The department suggested 17% A's. I give about 35% A's. The department suggested 50% B's. I give about 41% B's. And where the curve finally gives in is at the F range, which is 4%, and I beat the department by 1%. See, the F's are nice in a sense because one F takes care of a whole bunch of other shifting down of the grades. And it brings the class GPA down significantly. But seriously, you really have to try hard to get an F in this class. And in fact, I've never had a problem with a student complaining about an F. I've had problems with students who got C minuses, and they came and haggled with me to try to get a D or an F so they can repeat the class. And I don't cater to that kind of to that kind of request. If you get a C minus, you get a C minus, and that's the end of it. But people who've gotten Fs in the class in the past have been people who have just ditched on midterms and who have shown absolutely no engagement with the course. So it's very easy to decide their cases. I also make use of D minuses to make adjustments to the class GPA. D minus is essentially, you pretty much were on the edge of an F, but we're giving you a little boost up. So if you add up these numbers, 41 and 35, that's roughly 75% of the students who are in the A and B range. So take comfort in that. That's my suggestion. So if you're freaking out over your first midterm performance, keep in mind that the first midterm doesn't count as much as the other midterms. It's got a lower weight. And just let it be a warning signal that you should go and watch the webcast from the first or second lecture where I talked about study habits in the class that I suggest, and start implementing them. The earlier, the better. If you are overloading on courses, I want to warn you again. Please drop something between now and Friday. Taking one, ideally, I don't want you to take more than one technical subject, serious technical subject beside this one. Flaky technical subjects, that's fine. But no more than one other serious technical subject. A combination such as CS61A and EE20 will keep you plenty busy. And add to that the humanities or social science class. You'll be busy. So if you're doing more than that, you do it at your own risk. Don't come to me at the end of the semester and say, oh, I had 19 units and I didn't do well. I'll say, told you so, told you so. That won't help the situation. So please be realistic about your time management skills as they stand now. It may be that you can train yourself to be better time managers as you go forward. It may be that you learn how to walk on water as you go forward. But be realistic about where you stand now. Can you handle the load now, and are you doing it gracefully? Are you getting enough rest? Are you getting enough time to have a good time outside and balance it out with your coursework? If the answer is no, don't expect that you'll suddenly change with like a unit step and change your study habits, okay? Real world system, the unit step is an ideal signal. It never, so there's always a ramp up period. Some ramp up faster than others. And the only person who knows which part of that, what your slope is yourself. Nobody else can gauge that for you. So please be honest and realistic with yourself about what you can and cannot handle at this point. It's always good to train yourself to become better time managers and handle a bigger load. But you have this deadline of Friday to decide whether you want to stick it up in the class. I'd be happy to talk to you individually, but I'm not sure I can offer you much more than what I've said now. Yeah? This class is just going to get harder and harder. Yeah. The topics are going to get more complicated. In fact, today, when I talk about the continuous time impulse, you'll see how the class is ramping up. And when we get to Fourier series and Fourier transforms, things get sizzling. So part of the reason the first midterm was weighed less is that a lot of it was review material. Functions, sets, the complex numbers, these were supposed to be reviewed. Some of you have not had complex numbers before, and so this provided a time for you to catch up. But from this point on, if you're not comfortable with the material that we've been dealing with so far, knowing how to add things in the complex plane, how to draw things in the complex plane, and so on, then it's just going to get, the pit's going to get deeper and deeper. So realistically, this class just gets harder and harder as we get toward the end of the semester. That's the histogram, essentially, for the grades. And so you can see it's top-heavy. And part of the reason, ideally, if I could have it my way, I would like the class GPA to be pinned at 3. a B. Because I think that's basically what I can't talk from the point of view of Stanford, but I taught at MIT for a while, and I'm familiar with the undergraduate grading. So you guys are competing with your counterparts at Stanford and MIT, essentially. And I'd like you to be on an equal footing. And that's why I try to shift this up as much as I can toward a B. From my heuristic experience teaching those courses, teaching courses of this nature at MIT, I pin it at B, if I could have it my way. But life is full of compromises, and I have to live within the constraints that I have. So 2.9 it is. Sometimes I've gone a bit higher, 2.94, things like that, but that's about it. But this is essentially it. I mean, it's top heavy, so just be happy with that. And as much as I want to encourage you to always shoot for the highest grade you can get, in fact, I encourage you to do that unconditionally. I also understand that some people have different goals. This may not be the highest priority course in your schedule. I'm quite realistic about that. Many of you would not be in this class if it hadn't been required, which makes teaching this class and keeping it exciting that much more difficult for me. But do your best. I mean, shoot for an A, and then let the chips fall where they may. Okay? But be realistic. You have to be realistic about how many things you can juggle at once. If there are things outside of coursework that you can drop and still maintain a balanced life, and still do well in the courses, to do better in the courses, then do that. If you have to drop another course so that you can do better in the remaining courses, do that. And dropping a course is one of those decisions that nobody can make for you. It's a hard decision. It's also like deciding whether to do a course pass-fail or on grades. In my junior year as an undergrad, I once took a graduate course in error correction codes. And one term of it, I took it on, actually, the first term was info theory. The second term was error correction codes. And I changed it to pass-fail, and I ended up with an A+, and I was kicking myself. You've got to let the chips fall where they may. So be realistic and do your best. Another thing about study habits, which I may not have mentioned in the first lecture, is some of you have a habit of choosing a particular day to spend entirely on a course. You say, I'm going to do EE20 all of Saturday, and I'm going to do CS61A all of Sunday. That's not a smart way to study. I mean, you see how many breaks we take during an hour and 20-minute lecture. You need to have a mechanism to refresh your clocks and to reset your mind. And to think that you can spend 6 hours or 7 hours straight studying EE20 is just not a realistic and not an optimal way of studying. So what I suggest is this. If you want to spend your weekend to study for 2 or more courses, interlace them. Say, I'm going to study for 2 hours with 5-minute breaks every 20 minutes on EE20. And then we'll take a hike, make a phone call to somebody you like, do something that keeps your mind off of studying, and then come back an hour or 2 later, and then spend 2 hours on CS61A. Interlace them in this way, and you'll see that you'll retain the concepts much better. If you study, first of all, I don't think anybody has the concentration to sit down and study for 6 hours topics in a particular class. By the time you get to the 6th hour, you will have forgotten what you started off with at the first hour. So it's not a realistic way to study. So please try to implement these things and watch the webcast from the first lecture or second lecture where I talked about creating that table of techniques, problems, and their coordinates, and see how it works for you. Okay? Any questions? So again, I'm in my office from 2:30 to 4:30. Feel free to drop by. There's no sign-up sheet this time. So just drop by, and I'll meet with you according to your. Just keep track of if you're standing outside in the hallway, because I have to close the door. These are going to be private meetings. If you're standing out in the hallway, just keep track of who came first, who's on first, who's on second. All right. let us, I'll just turn this off. This was not a memorial service for somebody who just died. What's the story? Why all the gloom? Last time we were talking about the various properties of the discrete time impulse and its related signal, the unit step. Which is defined as, this is the discrete time unit step. Which is defined as 0 for n less than 0 and 1 for n greater than or equal to 0. We talked about how we can express the unit step in terms of the impulse. And one of those ways was to think of the unit step as a sequence of shifted impulses added together. So you had delta n plus delta n at 1 plus delta n at 2, like so. And this, of course, can be summarized in the infinite sum k equals 0 to infinity delta n minus k. So that was one way we wrote the unit step in terms of the impulse. Then we changed variables. And rewrote the sum. So if my new variable is L, and k goes from 0 to infinity, where does L go from and to? Negative infinity. When is L negative infinity? When k is what? When k is infinity. To what? N. So when k is 0, L is n. There's something I should point out at this stage. Notice we don't really care about the order in which we write these in a sum. So even though k equals 0 corresponds to L equals n, I'm putting the n at the top, and I'm putting the other limit at the bottom. When we are dealing with integrals, you have to worry about that order. So when you change variables, if this had been an integral and you were changing variables, then you would have had to put at the lower limit what the new variable would be for the particular lower limit value of the other variable. So if k equals 0, then L equals n would be at the bottom. And then minus infinity would be at the top. But here we're adding a whole bunch of values. We're summing them. And for summations, it doesn't make any difference. For integrals, you have to change the sign in front of the integral to reverse the order of the limits. So just keep that in mind. All right, so then we have delta of L. And this corresponded to the picture where you have L as your dummy variable. You have delta of L, so you've got a spike at the origin. And you're summing all the values of the signal from minus infinity to n. So these are all 0. And you can see that when you view the unit step in this way, if n is less than 0, you're summing a whole bunch of zeros, so you get a 0. The first instance where the first value of n for which this summation becomes non-zero is n equals 0. At that point, when I sum from minus infinity to n, what do I get? 1. And then after that, what do I get? 1, because I'm just adding more zeros to it. So that's exactly the definition of the unit step. So this is how they're related. And we also talked about how you can get the units, how you get the impulse from the unit step. You take the unit step, you shift it to the right by 1, and you subtract it, and that's how you get the impulse. And we wrote the relationship, which is kind of the analog of a derivative. This is a discrete time quote-unquote derivative. It's a adjacent difference of two values in your signal. Now, the impulse in discrete time has some nice properties. So, for example, if I have a signal f whose values are described by f of n, and I multiply this signal by delta of n minus some number. Okay, so here's my f of n. This is f of n. Okay, 0, minus 1, and let's say this is n. And I multiply this signal pointwise by delta at n. What am I going to get? I get what? F of capital N. Is that it? Well, when I multiply this by this, do I get a number or do I get a function? Is that a number or a function? So are you telling me that the function I get is constant? How would you draw this? When I multiply this by this pointwise, I take this and I multiply it. Tell me what to draw. So this is f of n delta of n minus n. How would I draw this? Zeros everywhere except at n. So I have zeros everywhere except at n. And what is the value at n? F of n at this value. And zeros everywhere else. So how would you, so this is obviously not the description for this function. What else do I have to add? Or what else do I have to insert in this description? Kronecker n minus big N. Right? That's what this is. It's a Kronecker at n of height, f of n. So this is an important property of the impulse. And it's called the sampling property. When you multiply a shifted impulse with a function, you pluck out the value of the function at the location of the impulse. Okay, is that clear? Excellent. So that's an important property. Another property is what we call the sifting property. And that is when you have a signal f of n coming in contact with a shifted impulse where the limits of the sum, I'll put negative infinity to infinity for now. The limits of the sum, you don't need negative infinity to infinity. All you need to do is make sure that the range over which you're summing includes n. But let's say it's minus infinity to infinity. What are you going to get? So this product we already know. Remember the mathematician's joke? Did I ever tell you the mathematician's joke? No? Ah. So when I was an undergrad, one of my friends told me this joke about mathematicians that I thought was amusing at the time, but it ended up having a serious impact on the way I teach and on the way I study. So they asked this mathematician, suppose you're sitting in the kitchen. You have boiling water in the kettle, and the kitchen curtain catches fire. What do? He says, well, I take the kettle and I dump the boiling water on the curtain. I put it out. Then they ask him another question. And the second question is, suppose you're sitting in the kitchen. There is room temperature water in the kettle. You haven't turned on the stove yet. And the kitchen curtain catches fire. What do? He says, I will boil the problem, and I've already solved that. I will boil the water, and I've already solved that problem. So, as ridiculous as that may sound, one of the ways I want you to study, and one of the ways I try to teach concepts in this class, is to build on what you've already discovered or learned. Okay, if you can convert a seemingly new problem into something that you've already solved, more power to you. Of course, the joke is a caricature of this process. I'm not asking you to increase your work or not use your brains. But if we've already solved the problem, let's try to convert. If you can convert a new problem to something we've already solved, let's do that. So we've already talked about this product. And what is that product? Actually, before I write equations, you should be able to tell me the answer. Because what I'm saying is, look at the product of those two signals and sum the values of that signal on the right-hand side, right here, from minus infinity to infinity. In fact, sum it from just before n to just after n. Whatever range you pick, as long as it includes n, you should get the same answer. So what would you tell me when you sum all the values from minus infinity to infinity? F of n. F of n. Okay? So drawing pictures will help you figure things out quite often. So by just drawing that picture, we figured out the answer. If you want to get a little more serious, you can say this is equal to summation. This product, we said, was f of n, f of capital N, delta of n minus capital N. Right? F of capital N is a number. It has no small n dependence. So I can pull it out. So I have f of n times the summation from minus infinity to infinity of n minus capital N. What happens when you sum an impulse over a range that includes where the impulse is non-zero? You get 1. This is 1. And that's another way to get to the answer. But the best way is doing it graphically. So we converted this into a problem we already knew how to solve. This is called the sifting property. So when a shifted impulse comes in contact with another function in this multiplicative way, and we do the summation over a range that includes this capital N, the impulse just plucks out the value of, spits out the value of the function at the location where the impulse is active. And this is called the sifting property. It's kind of like a sieve. Okay? You want a break or should we proceed? Can you people ever agree on anything? All right, take a 2-minute break. Okay, folks, let's come back to order. There is a family of functions that are related to each other in the way that the unit step and the impulse are related to each other. So let me start from one signal on this side, which is the doublet. Let's call it WD of n. This is the doublet, discrete time doublet. And the discrete time doublet, just like this delta was the 1 unit difference, first difference of the unit step, this doublet is the first difference of the impulse. What would this look like when I draw the lollipop plot? One up and one down. 1 at 0, and negative 1 at 1, and it's 0 everywhere else. Then you have the unit step. And then you have the ramp. Let's call it R of n, or let's call it ramp. Now, the unit step, we said, was the summation from minus infinity to n of the impulse. So what if we do the same thing, the summation from minus infinity to n of the unit step? Talk to your neighbors and tell me what you get. I've pretty much given away the house by giving the name to this function. But plot that function. Talk to your buddies. Are we done? Hello? Done? Up to you. Okay. Mm-hmm. Very good. So we have the unit step. Oh, actually, I should keep that as k. So I have u of k. It starts at 0, and it's all at 1. And you are considering 3 different cases. Okay? Why 3? Okay. I guess 3 is okay. Actually, 3 is better than 2. So 1 is n smaller than 0. So let's say n is here. The summation is 0, right? Because I haven't hit the first non-zero value of the unit step yet. So the ramp function is 0 for n less than 0. Okay? And now, what's the second case? N equals 0. So let's say n equals 0. And what's the value there? 1. Okay? And then n greater than 0. N greater than 0. N plus 1. And now you can see you can actually merge these two cases together. So the ramp is 0 for n negative, and it's n plus 1 for n greater than or equal to 0. And how would you plot that? So it's 0 for negative. Okay. So at 0, it's 1. At 1, it's 2. At 2, it's 3. And you can see why it's called the ramp. Now, of course, there's no end in sight. You can go in either direction as much as you want. The question is it going to give you anything useful? This one has an interesting interpretation. Let's say I'm looking at, let's call it doublet, actually, just to keep the bugging the OCD side of me, that we have a name for the other one, but not for this one. So let's call this doublet. So what happens if I multiply a signal pointwise by a shifted doublet? What do I get? How many spikes? Ooh, talk to your neighbors. Okay, how many impulses do I have? Where? At n, and what's it scaled by? F of n. And then what else? Minus f of what? N plus 1 delta n minus 1. Okay? So here you have your signal, f of n, and you're multiplying it by a spike at n and a minus that spike at n plus 1. So it clearly picks up the value of the signal at n and at n plus 1. This is the doublet, n minus n. And this is f of n. Okay? So it plucks out these two values. Whoa, put the wrong label there. This is n plus 1. This is f of n and f of n plus 1 right here. So what happens now if I sum from infinity to from minus infinity to infinity? N minus infinity to infinity, f of n, doublet, n minus n. What am I going to get? I have two spikes. When I sum over all the values, what do I get? How many terms in this summation are non-zero, potentially? 2. Which ones? F of n minus f of n plus 1. So again, this is a first order difference of the function. When we study convolution, you'll see much better what this doublet does. It's essentially a discrete time differentiator. That's what it is. Okay, now let's move to the more exciting continuous time story. And for that, I'll go to a new board. Get rid of this. So continuous time impulse, or the Dirac delta. This is a very different beast altogether. And the way I'm going to introduce this is by using an example from one of my favorite physics books. So let's take this example from the book An Introduction to Mechanics by Daniel Kleppner and Robert Kolenko. The continuous time impulse is inspired by a physical phenomenon that is observed often, and that is functions that are narrow in time and very intense in amplitude. Okay? So essentially strongly peaked functions, or in the case of physics, mechanics, strongly peaked forces. So the example is this. You have a rubber ball hitting a rigid surface. Okay? Rubber ball. Rubber hits the road. And let's say the rubber ball is 200 grams, so 0.2 kilograms. And right before it hits the ground, V down, or V impact, is 8 meters per second. Now, if you idealize the situation, if this is perfectly rigid, then this is actually minus 8 meters per second. We consider this direction is positive. So since the ball is initially falling, that's minus 8 meters per second. And at departure, it leaves at the same rate. Okay? You with me? Rubber ball hits the ground. The question is, what is the force that's exerted on the ball by the ground? We go to our favorite Newton's second law. F equals ma, or this is acceleration. If I write the acceleration in terms of the speed, or the velocity, I have m dv over dt. Right? Acceleration is the derivative of velocity. And in this case, I'm dealing with an object whose mass doesn't change as a function of time. So this m is constant. Let's take that inside. Okay, so I'm not talking about a rocket that's dumping fuel as it's going, as it's traveling, and therefore its mass is changing. I'm talking about an object whose mass is constant. This is what we know in physics to be the momentum. Oh, one thing I left out is the duration of contact. So the ball is in contact with the ground. Duration of contact. Let's say it's a millisecond. Okay, so now I have an equation that relates force to the derivative of the momentum. This is all review from your basic physics class, in fact, from high school. If you were to integrate both sides over the duration of the impact, so let's say the impact takes place from time t to t plus epsilon. Okay? Doesn't matter where you pick. I I can pick this to be minus epsilon over 2 to epsilon over 2. It doesn't matter. There's a center time, and the action takes place around that center time. So let's say the impact takes place from time capital T to capital T to epsilon of the force, which of course is a function of time. What do you get on the right-hand side? P what? Function of what? It's evaluated at where? T plus epsilon minus P of T. Okay? You with me? That's basic calculus. So the momentum just at the time of departure minus the momentum at the time of impact. And there's an epsilon time duration between the two. What is the momentum at the time of impact? What's the momentum? Negative? You know, England for me is a second language. You need to speak with me clearly in plain England. I don't understand these dialects, okay? Don't talk to me like you're from the Appalachian. What's the number? Negative 1.6. And how do you get that? Negative 8 times 0.2. Kilogram meters per second. And what's the departure? Positive 1.6 kilogram meters per second. Okay. So the difference between so you have the integral from t, in our case, t plus 10 to the minus 3. Epsilon in our case is 10 to the minus 3. That's the duration of impact. Of the force is what? What's the total? 3.2 kilogram, meters per second. All right? So notice what's important here is the area under the force. I'm integrating the force over a certain time period. The area of the force is what's important. So here's T. Here's T plus epsilon, and this is a very short time interval. Now let's say the force takes on some shape. Okay? It peaks at the center of that time interval. So this is at the point of impact, and the ball gets compressed a bit, and then it leaves. So it has some kind of a shape. I don't care what shape it is. So this is F peak. Okay? Let's approximate what the average force is over this time interval. Average force would be, you draw a rectangle, and you'd say, well, maybe it's not that high. You'd say F average, and duration is epsilon. What is F average times epsilon? Huh? It's 3.2. Right? So the area under that rectangle, I'm saying, is the same as the area under that curve, whatever it is. So I'm not even worried about the peak. What is the F average? Now, epsilon is 10 to the minus 3. Can you figure out what the F average is? 3,200 newtons. 4.45 newtons is approximately 1 pound. So that works out to what? 700 something? 720 pounds of force. And that's just the average. A heck of a lot, eh? Now, I've ignored gravity, but if you actually go to the book and they continue this example and they incorporate gravity, and it ends up not having too significant, in fact, it's a negligible impact on this average force. That's a heck of a lot of force for a 200-gram ball. Now, imagine if this is the average, what the peak is. So this notion of strongly peaked functions that occur over narrow time frames occurs again and again in the physical world. And the continuous time impulse is inspired by this phenomenon. It's an idealization of this phenomenon. Notice in this whole example, what's important is the area under the force. It's this area under the force that real-world systems respond to. Suppose Meatball has, do you want a clunker or do you want a clunker? So Meatball has a clunker, and who wants the Ferrari? You are? Jonathan. Jonathan wants the Ferrari. Meatball has the clunker. Okay? They both start, so this is Jonathan. And this is Meatball. They say, okay, let's race. Well, I withheld that critical piece of information from you before I asked you if you want the clunker. So they want to see where they end up at after 5 seconds. Okay? Maybe I should, let me redraw this a bit. Since Meatball is going to have the shorter. This is Jonathan. This is Meatball. So they both press the gas pedal for 5 seconds, and then we see where they end up. So Meatball goes. Presses the gas pedal, at 5 seconds it releases the gas pedal. Okay? Jonathan presses the gas pedal. Which one has the greater area? Remember, the area is what determines what happens to the momentum. Momentum at the start for each of them is 0, because they're not moving. V is 0, so mv is 0. At the end of 5 seconds, at the 5-second mark, then we measure their momentums. Let's say the clunker weighs exactly the same. Meatball's clunker weighs exactly the same as Jonathan's Ferrari. So the masses are not different. The only thing that's different is the amount of force that Jonathan's engine can produce, compared with the amount of force that Meatball's clunker can produce. The end momentum is determined by the area of each of their respective force curves. So this is the force. Force, Jonathan as a function of time. This is force, Meatball as a function of time. Okay? Real-world systems respond to areas under the curve. Now, ideally, if you idealize this to a zero-duration curve, can you have a finite height and still change the momentum? Let me rephrase that. Suppose you want to change the momentum of an object instantaneously. in 0 time. Okay? In other words, that epsilon is 0. What would the height have to be for you to have a non-zero area under the curve? Infinite. And that's exactly what the continuous time impulse is all about. So the continuous time impulse, so let me just write some of the stuff I've been saying. To change the momentum. See, in the case of the rubber ball, the momentum changed in the course of 100 milliseconds. Or, sorry, 1 millisecond. But if we want to change the momentum instantaneously, i.e., epsilon is 0, the duration is 0, then we must if the curve only peaks up to a finite value, the area under it will be 0 width times a finite height. You get 0. So the height, the height of the force function must be infinite. Otherwise, you can't do it. And of course, in real world, you can't change the momentum of anything instantaneously. And there are electrical analogs of this. So can you charge a capacitor instantaneously? No. But you can have a signal that ramps up the charge pretty fast, fast enough that you can approximate it to be instantaneous. And the only way to do that is with an impulse input. And that's what the Dirac delta is all about. So let's put it on the board once and for all. Put this. Ooh, we're almost out of time. So the Dirac delta is the idealization of what we just described here, where the width of this function decreases down to 0 and the height goes toward infinity. So, but the area, we normalize it to be 1. So this 1 is the area or strength of the impulse. It's not the height. If you want to talk about the height, delta of t would have to be infinity at t equals 0 and 0 elsewhere. This is not a proper definition of a function. It's not a useful definition. So, as I said, I think I said it earlier. If not, I'll just say it now. When it comes to the continuous time impulse, we don't care about what it is, but we care about what it does, how it behaves when it comes in contact with other functions. What we do know about this impulse is that if we integrate from just before to just after, we get 1. In fact, if you integrate from over any interval that includes the location where it's non-zero, you get 1. So we normalize this function to have unit area. And the way we do this is the following. We can think of the impulse as the limiting function of a variety of other signals that we can define more nicely. Suppose I have the following pulse. I have a pulse that goes from minus delta over 2 to delta over 2, and its height is 1 over delta. Okay, I call this delta sub cap delta of t. What's the area under this curve? 1. You unit area. Okay? One way to think about the impulse is as the limit delta goes to 0 of this finite width pulse. As delta goes to 0, what happens to this box? It gets narrower and taller. Does the area under it change? No. The area under it stays constant. So you can think of the Dirac delta as a limiting case of this. I can also define it in this way. A triangle from minus delta to delta of height 1 over delta. All right? This has unit area. And as I take the limit of this, I get something that's narrower and taller. And since you're always infatuated with the bell-shaped curve, I can also define the Dirac delta using the bell-shaped curve. So here's a bell-shaped curve, or the Gaussian. If this is a probability function, its standard deviation is sigma. I can define delta delta as 1 over delta square root of 2 pi e to the minus t squared over 2 pi delta squared. In probability, you can show that this curve has unit area. It's not obvious when you look at this, but it can be proven that this has unit area. And the height at the origin is what? What's the height at the origin? Plug in t equals 0. 1 over delta square root of 2 pi. So the thickness of this curve depends directly on delta, and its height depends inversely on delta. So when delta goes to 0, you can again think of this as the Dirac delta. Okay? It's precisely because you can define the Dirac delta in so many different ways that we don't actually care about what it is, what the exact shape of it is, and what the description is. We care about what it does to other signals when it comes in contact with them. And we'll talk about that next week.